So our learning target was to identify phase changes in a chemical system. So when we looked at that grid, that specific grid, we could identify, okay, where was the phase change occurring at? How did we know that? Yeah, well, what do we call that? The flat line, the plateau right there. We knew that at the plateau, we have a phase change occurring. Now, as I quickly click over to our success criteria, we need to be able to describe the kinetic molecular theory of matter and how it relates to phases of matter. Now, let's break that down a little bit, okay? What is kinetic energy? Kinetic energy, Tyler? Okay, what's the difference? What's the big thing between kinetic and potential energy?
Potential is like when something's like still.
Okay. Okay, kinetic is when it's moving. Potential is when it has stored energy. Okay, so when we're talking about this kinetic energy, we're going to talk about things that are moving. And when things are moving, how do we relate that to temperature? We did that in the gizmo. How do moving things relate to temperature? What do you think, Paige? The higher the temperature, the faster they're moving. So when we're talking about this kinetic molecular theory of matter, we're going to talk about movement of the molecules. Okay? Our second success criteria there says to explain how matter can change from one phase to any other phase and how these require energy. So that right there, that's going to be using our grid, using those 5 quadrants. So as I look here at my kinetic molecular theory of matter, okay, all particles have energy, and that energy varies depending on the temperature. If I have a higher temperature, I have more kinetic energy. If I have a lower temperature, I have less kinetic energy. Okay? And that is what determines whether a substance is a solid, a liquid, or a gas. Okay? Like I just said, solid particles have the least amount of energy. They are moving the slowest. Gases are moving the fastest, so they have the greatest amount of kinetic energy. The temperature of a substance is the measure of the kinetic energy. Changes in phase occur when the energy of the particles change. So as I get those molecules moving faster and faster, I can change the phase. Well, how can I do that? If I add a certain amount of energy. Okay? There are spaces between particles of matter. The greater amount of empty space occurs when we go from a solid to a liquid to a gas. Okay? So as we are changing the phases, we are getting greater amounts of empty space. There are forces between atoms and molecules. They become stronger as the particles move closer together. These forces are what we call intermolecular forces. So, where are we going to have atoms and molecules closer together? What type of state? What type? A solid. Okay? So, will there be greater intermolecular forces between solids than there were between liquids and gases? Yeah. Sure there will be. Okay? Now, go ahead and copy. This is our first phase change problem that we're going to work, other than what you did in your notes. So go ahead and copy this down and then we'll talk about it. My problem states how much energy does it take to raise the temperature of 19 grams of water from minus 13 degrees Celsius to 55 degrees Celsius. Now, probably to be more specific, if I've got negative 13 degrees Celsius, okay, what state of water is it going to be? It's going to be ice, right? Because we know that when we're dealing with ice, we're dealing with water, this flat line right here, that flat line right there is the melting point. And at what temperature is that going to be? 0 degrees Celsius, correct? What's my other flat line right here going to be? What do we call that? The, Cody? Boiling point. And what does water boil at? Remember? 100 degrees Celsius. Now, notice at those flat lines, when we're changing the phases, do we have temperature changes? No. So those are where those flat lines are occurring. The temperature remains constant until that changes from a liquid to a gas, from a solid to a liquid. So if you look at my equations up here, do you see anything to do with a change in temperature? You do not, because delta T would be 0. There is no change. Okay? So that's where we use the heat of vaporization and the heat of fusion when we have those different changes in states. Now, if we look here in quadrant 1, I'm increasing my temperature till I get to 0. Quadrant 3, I'm increasing my temperature till I get to 100. Quadrant 5, I'm increasing my temperature there. So we do have changes in temperature in 1, 3, and 5. So that's why we have the delta T. Now, this particular question that we're talking about, we started at negative 13 degrees Celsius, correct? So we are starting in quadrant 1. Where is our final temperature? Okay, what is our final temperature, Caitlin? On the problem, you just wrote it down. 55 degrees Celsius. What quadrant does that fall into? What number? Yeah, Stephen, what is it? 3. Quadrant 3 right here is 55, because up here, quadrant 4 is going to be 100 for water, right? So we're going to go quadrant 1, quadrant 2, quadrant 3. Do we need anything for 4 and 5? No, we don't get to those quadrants yet. So we're going to use these 3 equations. Right here, Q equals MC of a solid delta T. Q equals M times the heat of fusion. Q equals M times the specific heat of the liquid times the change in the temperature. So what you're going to see is these calculations aren't terrible if you know what you're looking for. All right? So let's start out with quadrant 1. Quadrant 1, the amount of energy is going to be equal to my mass times my specific heat of a solid times my delta T, my change in temperature. Now let's talk a little bit about, let me pop it up here. Let's talk about, where's my taskbar? Right here. No, here. Here we go. Let's talk about this right here. As I'm looking at this, I have my heat of fusion right here. I have my heat of vaporization, melting point, boiling point. Okay? So I don't always have to use water. We could adjust this to some different things. Most of the time, you're going to see when we're dealing with this, we deal with water. So we're going to have our heat of fusion, and even though our heat of fusion here, you should have that circled right there, and it won't let me circle on my board here, but you should have that in joules per gram, right? On your table. And over here, you should have same thing, joules per gram. So basically, When we divide both of those by 1,000, it's going to come out to be the same thing. Now down here at the bottom, I'm looking at these values right here for water. Okay, so here is my specific heat. Now look at the label. The label's joules per kilogram times degrees Celsius. We don't want that. We don't want it in kilograms, so we're going to divide each one of those by 1,000. And I've already done that on your chart, right? Instead of having 2,100, 2,100, you should have 2.100, correct? So I've already done that for you on your charts. So right here are the three main ones. Here's the specific heat of a solid, which is ice. Specific heat of a liquid, which is water. Steam has a specific heat of 2.010 joules per gram degrees Celsius. So when I come back here, and I say, all right, what is my M? Well, M is the mass. What is the mass of water that I have? Carly? 19.0 grams. What is my specific heat, Carly, of a solid? (2.100 joules per grams times degrees Celsius). Now, the very last one, change in temperature. Final temperature minus initial. What is my final temperature in quadrant 1? My final in quadrant 1. We're going to the freezing point, right? So it's 0. So TF is 0. What did I start with? Negative 13. So 0 minus negative 13 gives me 13, right? So when I put this all together, here we have our different values that we're going to be multiplying together. As I multiply that together, it comes up to a value of 518.7 joules. I am not going to sig fig this until my very end, okay? I'm going to get all these values, and I'm going to worry about sig figs when we end it, okay? So now I've got quadrant 1 done. I'm going to move on to quadrant 2. What's my equation for quadrant 2? Q is equal to M times the heat of fusion. Okay? Well, what is the heat of fusion of water? 333 joules per gram, right? So, my mass is 19. I multiply that by 333 joules per gram, and I come up with a value of 6,327 joules. My third quadrant just happens to be my last quadrant for this particular problem. Okay? I'm going to take Q, and I'm going to Q is equal to M, the specific heat of the liquid, the change in temperature. All right? Carly H, what is the specific heat of a liquid? (4.186 joules per gram times degrees Celsius). Okay? What is my change in temperature? What temperature did I start with, Madison? In quadrant 3. What was at the very bottom? Where did we start? Huh? 0. We started at 0. So our initial 0, where did we finish? 55. So 55 minus 0 is going to give me 55. So I take my 19 times my 4.186 times my 55, and I came up with a value of 4,374.37 joules. So I have calculated each one of those 3 quadrants individually. Now I'm going to go back and I'm going to add them together to get my total. So here's quadrant 1, here's quadrant 2, Here's quadrant 3. Now, you're going to see that I put 4 and 5 up there, but I didn't need to because they were both 0. We didn't hit those quadrants, okay? When I added them all together, I got 11,220.07 joules. I jumped my decimal place 3 to the left to put it into kilojoules, so it's 11.22007. Now I'm gonna sig fig it. When I sig figged, I am going to use my sig fig to be 19.0. Has how many sig figs? 3. So I'm gonna 3 sig fig it. 11.2 kilojoules. Now, my second problem. Go ahead and copy this down. We'll work it. My question states how much energy is released when the temperature of 5.00 grams of water vapor changes from 105 degrees Celsius to negative 10.3 degrees Celsius. So a couple of things to think about here. We are starting out with steam. Okay, water vapor at 105. So that's going to put me in quadrant 5. We're going to negative 10.3. So it's going to be in quadrant 1, a solid. So are we actually gaining or losing energy? We're losing energy, right? This is cooling off. My kinetic molecular theory of matter is going to be going slower. So my temperature is decreasing. So we're going to see a loss of energy. Now, as I come through here and I look at my different quadrants, we stated that we are starting all the way up here in quadrant 5 at 105 degrees Celsius. We're ending down here at 10.3, I believe. 10.3 degrees Celsius. So we are going to need to have calculations for all 5 quadrants. Now, it's not tough because we can read data tables and we can add and subtract. So, in quadrant number 5, Q is equal to M, the specific heat of the gas, the change in temperature. M is 5.0. Specific heat of a gas is what, Aiden? 2.010. My change in temperature. I started at 105. Where did I end at? 100. So 100 minus 105, is that going to give me a negative value? Absolutely, because I'm losing energy. So that negative value signifies that I have lost energy. My second quadrant, or excuse me, check. My fourth quadrant is going to be Q is equal to M times the heat of vaporization. Now, the heat of vaporization is 2,260. My M is 5. Now, the part about this, once again, folks, you can think about it this way. We are losing energy, right? So, my value has to be negative. Could I think of this as negative 2260? I could. I probably should. I don't have that in there, but I could. So my value is going to be negative 11,300 joules. So in quadrant 4, I have lost that much energy. Quadrant 3. Quadrant 3. Q is equal to M, the specific heat of the liquid, change in temperature. Once again, my M is 5.00 grams. My specific heat of the liquid is what? Amelia, what is my specific heat of the liquid? 4.186. My change in temperature in quadrant 3 is, What's my initial temperature? 100. What's my final? 0. So what's 0 minus 100? Negative 100. I have my negative value there. When I multiplied all of those together, I came up with 2. Negative 2093. Now we're into the second quadrant. Quadrant number 2 is the heat of fusion. Now, I'm going to get Q is equal to M times the heat of fusion. Remember, we can think about my heat of fusion as being negative. So my value for the heat of fusion's water is 3, 3, 3. So, like I said, I probably could have a negative value right in here to signify that this is losing energy. So that 5.0 times 333, I know I'm losing energy. It's going to give me a negative value, which is negative 1,665 joules. Now I'm finally getting to my last quadrant. So this is going to give me long problems, but like I said, they're not terribly tough with the math. So I look. My final quadrant says that M is equal to C of a solid delta T. My mass, once again, is 5.00 grams. Specific heat of the solid, it's going to be the specific heat of ice, 2.100 joules per gram degree Celsius. My delta T, okay, I started at 0. I ended at negative what? So negative 10.3 minus 0 is going to give me negative 10.3. Excuse me. So I multiply those together, I get negative 108.15. Now, what's my next step, Paige? Add them all up, right? So I have quadrant 1, quadrant 2, quadrant 3, quadrant 4, quadrant 5. I added them all up to get negative 15,216.4 joules. Or, when I converted to kilograms, negative 15.2164 kilojoules. Go back to my original problem. How many sig figs? 3 sig figs. So we're going to put that at negative 15.2 kilojoules. Now, I got to show you one more type of a problem because you're going to see this on your WebAssign. Okay? So go ahead and copy this guy down and then we'll work it. My question states, how many grams of ice at 0 degrees Celsius and 760 millimeters of mercury could be melted by the addition of 2,500 joules of heat? Now, as I'm looking at that, if I am melting something, which quadrant am I going to be in? What do you think? About 2, right? So in quadrant 2, my equation is Q equals M times the heat of fusion, correct? So I'm going to use that to calculate how many grams. Now, this 760 right here, millimeters of mercury, that is a pressure. This 0 degrees Celsius, what is STP? 0 degrees Celsius, 1 atmosphere of pressure, right? Well, this is what 1 atmosphere of pressure is equal to in millimeters of mercury. So if you don't have that written down, jot that down somewhere in your notes, that 1 atmosphere of pressure is 760 millimeters of mercury. So all of those values that they're giving me there, That's just telling me I'm at STP. Don't really need those to calculate this problem. What I need is to switch. I need this right here. Q is equal to M times the heat of fusion. So I'm in quadrant 2. Right there's my equation. I am going to manipulate this to solve for M. So M is going to be equal to Q divided by the heat of fusion. What was my Q? 2,500 joules. What is my heat of fusion of water? 333. So when I divide those out and I cancel my labels, I'm going to have grams. And when I divided that out, I got 7.508 grams. Notice here that with this decimal point behind that, I have 4 significant figures. So when I'm doing division, my final answer has to have 4 significant figures. So at STP, if I have 2,500 joules of energy, that tells me that I can melt 7.508 grams of water with that amount of energy. Okay?